Hello everyone and welcome to another episode of No Orientation Programming. I'm Joe and today we will code something quite interesting. Last time we didn't start this thing because it's quite heavy. Hopefully today we have some progress on it. What do we want to do? In our software system, in any system in the future, we want to execute external programs on the Linux system because we want to use the rest of the system. The Linux system is very feature rich if you are able to communicate with other processes. Especially if it's convenient for us to communicate with these processes, then we are using this possibility, this opportunity. And I'm not talking about stuff like, I don't know, named pipes or sockets. We should be able to communicate with the basic mechanisms that are provided by the operating system. For example, the std in, std out, and the standard input, standard output, and standard error, as well as the signaling system. And this is the goal for today, to provide a process class which gives us control over the input, the output, the error, and the signals. Yes, and that's it. So we have a lot of work to do because we have to invoke a lot of quite heavy functions like fork, pipe, fork, duplicate, and exec. These functions have very long man pages because especially fork, I think, and even longer the clone page is very long. The clone function call is telling us quite a lot. Let's do something. I want to next. Here I want to have Linux GitHub. I want to have the source code of the most important stuff, like Linux, of course, and clone, come on, yes, fine, and glibc and GitHub. Does this make sense? Do we have the source of the GNU C library? emui kernel, glibc. can we download this thing, unofficial mirror of software? Okay, let's check this out. It's not hosted on GitHub. Because of because of the GNU, I guess. Okay. But that's fine. I want to see the most important places for the functions of fork. I have seen on I don't know at which place, but I've seen on Stack Overflow that we have to be careful to know the differences between these functions. They are doing different things, but some are similar and like that. For example, I think there are many phrases and words we have to understand if we want to execute another program on the Linux system. Then we have to make a fork. That's fine. I have Plandormal life. Plant tech, yes, I think that's it. I will donate someday. This is a very useful tool. The online thing is very, very useful. Okay, subs fetch wait. Okay, photo. Okay. So, we have the function fork. At first, what do we have? We have our parent process. Proc parent. Let's see. Okay. Forking. File executing and then forking. Okay, we have a parent process. And this process that's our program 1. And this thing contains 2 other things. Plandormal component diagram. Oh, come on, yes, got it. So, what do we want? Okay, this is a frame. Okay, let's call this a frame. And we have 2 sections, essentially, I think. That's the code section. Okay. Okay, and then we have the Whoa, what the hell is happening? Whoa. What the hell is happening? Okay. Computer started to freak out. Okay. Component. And we have a code section and a data section. Data. And we want to align this thing. Code hidden data. Why? What? Because I think I need this. Yes, fine. Okay. And we may have or should we this should tell us the content of the RAM, the random access memory, and then we have the kernel. Should we call this a group? A node. Should we make a node? I don't. Yep. Let's make a node. This is the kernel as kernel 1. Can we do this? Because that's, yes, cool. And then we have proc parent hidden. Actually, no, I don't think we need this. At first, we have two components. Component thread 1, for example, as thread 1. Yes, that's cool. And we have another thread. Perfect. What the hell am I doing? Oh, no, yes, fine. Okay, cool. And we want these two threads. Both of them are reading the code to thread 1. Yes, and code to thread 2. Both threads are reading, and both of them are writing to the data section. Perfect. And the kernel has other information about the process. For example, the kernel has, let's make a different shape. like a database. Oh, database looks good. A database, these are the file handles. And let's say thread 1 okay, the kernel has let's do something else. For example, what does a thread have? Here inside we have a database of stack. Yep. That's not intended. That's not fine. Does not look good. Oh. Okay. We have a stack. And we have a program counter. Ah, yes. They solved this. This is killing the CPU. Okay. Hopefully we do not lose any frames. Okay, what does a thread has an information? I think we have a program counter and a stack. And data. Data has uninitialized. And then we have initialized, and then we have the heap, I think. Oh yes, that's fine. That's fine. Okay. So we have the code section and the data section. The data section contains the uninitialized section, the initialized, and the heap, I think. Both threads can write to the data area, and they both can read from the code area. This is the reason why we have to synchronize the write access from different threads. Because if thread 1 writes to this thing and then the kernel switches the thread, then we have to tell thread 2 that there is a write access at the moment, and we have to keep away from stuff that is accessed by thread 1. So every thread has to know at which point it is, and each thread has its own stack. Thread 1 may be the main thread. Let's indicate this main. And here we have a worker. for example. Okay, and the kernel holds file handles. The code uses some Linux functions, and if, for example, the process is opening a file, then the kernel stores the file handles. For example, file handles can be std out, std in, std out, standard error, sockets, other files, sockets, and maybe other stuff. So quite a lot. So we have the file handles, which can be standard in, out, error. Let's make this in one line because it's too. This is this group can be seen as one. And then we have another other files. From the file system, we can have sockets and other stuff. Okay. Now, what is happening if we do a fork? Okay. Then we have, I have to write code 1, data 1, code 1, data 1. Let's call this proc 1. Now I think I will get the mess. Here I have kernel 1, that's fine. Kernel thread 1.1. Wow, I think this will be bad. I'm quite sure that I'm not changing this without an error first. Okay. Code 1, thread 1.1, thread 1.2, thread 1.2, hopefully. Cool. And then we have the same thing again. But 2. No. 2. Yes. Now, if we fork something, then program 2. So yes, that's the child. This is the parent process, and that's the child process. But it's still containing program 1. So we have, let's call this code 1, data 1. I think that's okay. Program 1. So essentially we are cloning this. So this is the function clone. and it's quite obvious. It's cloning the stuff, but it's not, so it's, it makes a copy of the process. And then let's make, hopefully this is working. Kernel 1 to the right, kernel 2, and we say fork. Here we have the fork. It's completely, that's very, very strange looking. Proc 1, maybe it's better if we use proc. No, it's, why? Why is this happening? I don't know. So, I don't care. Okay. So we have a clone of the entire program. That means, oh, okay, file handles. Then we have something else. That is, we have the file handles, but we also have, okay. A task structure. This is the task structure. The kernel. Oh, let's make. Oh yes, oh yes. Oh, that's better. This looks quite cool. I want to have for thread 1. I want a node. No, not a node. A frame. I want a frame. Oh, the style is different now. Okay. Well, looks kind of cool. Yes, whatever. Okay, but essentially all of these things are bytes in memory. File handles. Oh, What? Why? Database. Why can't we do this? What's wrong with creating a frame? Okay, that seems to be a bug. Okay, database, whatever. Okay. That's too long. Hopefully this is better. Okay, because I want to have another thing here. No. I want to call this task 1. Okay. It's getting quite big, but hopefully. Okay. But okay, fine. For every thread, I think of a process, the kernel has one task structure. We will look for the task structure. Task 1, thread 1. This is the information of the process in the kernel. But if we fork a process, then the kernel does not copy everything, because, for example, this second thread is not used. Yes, oh, that's better. Oh, yes, we have to remove thread. Yep. So the function called fork makes a copy of the process, because it's a version of clone. It makes a copy of code. It does not make this copy immediately, so it's not. It does not make a copy immediately, but at the beginning they share the memory. I think the code is just referenced, because the code should not be changing. Only the data sections. If we have a copy of the child and we are modifying the data section in the child, then only at the time instance when we change this memory, then the data gets copied. Okay. So the file handles stay the same. Yes. Okay. Okay. Now we want to be able to communicate. Files. Oh yeah, very important. Files. This was the most important one I did forget. That is sockets and maybe pipes. Sockets and pipes. And that is what we do first. We want to be able to communicate with our child later on. And we have 3 connections. We want every process has standard in, standard out, standard in, standard out, and standard error. Usually, but for our child process, for example, if we create the parent process in the terminal and for example git, if we start git, then if git writes to standard out, to the file standard out, then we see this text. So this text was written to standard out, and we are able to see this text. So the file, the output file is this screen. Every program can write to this screen. If we create a child and this child is doing something, then it's all using the same file, our screen, but we don't want that in every case. So we have to remove the standard out from the child. We have to exchange the standard out with something else. Okay. Or substitute with something else. Okay. So this is the parent process having process 1. I want to make an error. An error. Line group. How can we achieve this? Maybe we could. Oh, okay, let's try something. Okay. That is hopefully this makes sense. Data code. No. It's not doing the thing I want. Yes, but no. Yes, that's fine. So we have a symmetric version of the diagram. That's okay. That's cool. And now I want to have an error between. Hopefully this is working. Code 1. No, right. And then code 2. Okay, what about proc 1 and proc 2? Maybe I used the wrong error. See, that's so bad. What the hell? Okay, so we have to use code 1 and code 2. That's a weakness of plant.ml, unfortunately. Okay, and this is connected by fork. Yes, it looks better. Can we do the same with proc 2? Oh, yes, okay, yeah, I think that's cool. We have the fork, yes, yeah, that's cool. The fork, the call to the fork function is embedded in the code, and the result of the fork function is this entire thing. But it's still confusing. It's still confusing because I want to make Yes, okay, we make a node situation 1. No, that's not cool. Okay. Yes, no, that's still better. We have to make this quite clear. Okay. As proc 1. And here we have a frame that is called user space. User 1. And then the kernel. Yes, that's cool. And now we make a frame. The kernel is a frame as well. Yes, that's cool. I think that's better. Okay, so. And then we have another program. It's called Procto. That's the child program, but the child process, but program 1. And yep. So, and this is the user space of user 2. Okay, and then we have make all of this again. Okay. Yes, that's cool. We have our parent process, the program 1, which is the combination of the user space and the kernel. I call it the user space, but yeah. Good enough, I think. Oh, I'm missing something. I'm missing the chat. I'm missing. Oh, that's cool. Nobody wrote something. Okay. So this is the situation before, and then additionally, yes, So this is not another situation, but at first we only have this, and as soon as we execute the fork function, then we have this additionally. We have another process in the Linux kernel with another task structure. We should not call this task 1. Just one task in the kernel. We have one task in the kernel. Here we have the program 1 parent process. We have the parent process with a certain process ID. Yes, we could say that we have no. Yes, I think every task has a process ID as well. Okay, so thread 1 has a P stack and a process ID. Oh, that's not good. Program. Let's make it different. Come on. Hopefully my model makes sense. If not, please tell me. Okay. we have one process with a certain process ID. Every thread has a process ID, task ID, I think. And if we fork a process, then we have the copy of the code, the copy of the data section. We have all the file handles like before, but there is one thing different. We are not getting the state of all threads. We are just oh, yes. That's important. I don't want to make this error here, but I want to make this error somewhere else. That is thread 11. Oh, come on. Yeah, that's so bad. That's so bad. Yeah, whatever. Okay. So, actually, any thread the thread which is executing the function fork is creating another process, and this thread is used as the main thread in the next process, as soon as I understand. So this thread is making a child, actually only one thread, and we have a duplicated data and code section and all the file handles for the entire process in the kernel. But this also means that if we have a certain state in the data section, for example, thread 2 is locking a mutex in this section, then it is also locked in this section, but there is no second thread anymore which could unlock the mutex. This means this data section is not very reliable. It's just it's existent. It's existent in the child process, but we have to be careful what we are using in this section. We can't just move on like before. So we have a certain state after the fork. If we want to, yes, then we have the open file handles. And if we want to be able to communicate with the child process, then we have to use the pipes. That means before we make the fork, we create the pipes in the parent process. This means in the code, the first thing we are doing is creating a pipe. If we create the pipe with the function pipe2, pipe, then we get two file handles. We get the file handle to the write end and to the read end. And if we make a copy from one process, then we use a pipe to communicate between these two processes. For example, the parent process can write in the right end of the pipe, and then the child process is reading from this pipe. Okay, So that's the first thing we will do. Let's make something like this. Okay. Documentation system. Fuck. Okay. Maybe this is... It's better to... Files to make something like this. Yes, I think that's better. A smaller version. Okay. 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 So this process is a clone of this process, but a little bit simpler version of it. Okay. Now. In our file executing process, we are starting in the start state, and then we are going to the pipe creation state, and let's test something. I want to see if we can compile this. This statement may fall through. I want to disable this warning. Expect the marker comment on its line. Yeah, fall through. The marker has also come right before the case label. There cannot be an independent closing brace. Okay. Fall through is among the markers which fail. False. Oh, that's interesting. Can we disable this thing? Hopefully. Let's test. That's the unit test. Unit test file executing. Do we have fall through? Oh, implicit fall through. Just remove this thing. This statement may fall through. Okay. No implicit fall through. Yes, that's cool. Because that's something I want to... I want to be able to fall through. Like this. Okay, that's cool. I want to use the same fall through implicit fall from I want to disable this one. Okay, for the main project as well. Okay. The first thing we are doing is creating a pipe. If we cannot create the pipe, then we return with an error. Then otherwise we move on and we have a set of 2 file handles in the structure pair of file descriptors standard in and it's always read and write, the read and write side. I don't want to use an array of file handles because I don't want to access these two file handles with 0 and 1. I want because they have a certain meaning. So I'm using fd read and fd write in the struct. This is the same, essentially. Okay. And then I just give the pointer to the first element instead. It's the same like here. Okay. So the next thing we want to do is we want to create another pipe. We want to create 3 pipes. 3 pipes. That is 1 for standard in, 1 for standard out, and 1 for standard error. So if we have an error in one of these, in here or here, then we have created a file handle. But at this point, we are exiting the process. If we do this, then we are shutting down the process and we have one open file handle. We have to close the file handles. Could not create pipe for std in out and error. So then if we exit the process at this point, then we have to close the pipe. Okay, this means in the shutdown state machine we have pipe pipes create, and here we have pipes close, and here we have to initialize the file handles. To -1 each, and then we say what is the return value? On success, 0 is returned, on error -1 is returned. Error is set to indicate the error and pipe is left unchanged completely. On Linux, another system pipe does not modify pipe if they on failure. A requirement standardizing this behavior was added in the Linux specific does not modify on failure. Likewise, okay. So if there is an error, then we can be sure that this has not been touched. That's okay. But we have to I want to add this thing. I want to see the official system. Ah, error. Oh, come on. What the hell? Ooh. I think the beer kicks in. Okay. Could not create pipe for standard in. The reason is some error. Okay. That's cool. This means in the shutdown function we can say, hopefully, we can say if the file descriptor read is bigger or equal than 0, then we can close this pipe. If I want to create a pipe and then I want to create a close pipe. So we have to close the pipes. Okay, let's do it like that. Because we will close this one side in every case, and we cannot know at okay. So we have to check every single element. That's okay for me, but we should void pipe close, and then we have the point a pair of file descriptor pointer pair whatever if not pair p pair then return, otherwise p pair pair. Oh, come on, stop. Yes, I think that's okay. And then we can make pipe close to every pipe, and then very important, very important. We have to give the close function the file descriptor, of course, and then we need this thing. Yes, and let's make a pipe in it. Come on. if not return, and then we say p pair fd file descriptor read is equal to -1. Right. Read is -1. Fd write. Okay. Yes, that's fine. So if this file pointer has a valid ID, if this file handle has a valid ID, then close the file handle. Okay. So if only one side of the pipe is closed, this function is working, and it's working if both of them are closed as well. Okay. Yes, so we have, yes, this strange thing, pipe init. And that means we can use, in the shutdown function, we can use pipe close perfect. So in any case, if something goes wrong, we have initialized the pipes, and if something goes wrong at any point, we are exiting the process with an error. Exiting with an error means the process gets shut down and then is in the shutdown process. We check the state variable, which is one of these. If so, none of the shutdown states, then we say, okay, this is the shutdown beginning, and then we move here. That's cool. So we should be able to start this thing, and then okay, it somehow, yes, because what? Oh, yes. No, I don't understand. I should be able to close the thing. That's bad. One moment, please. So the reason why I was not able to close the program, because we have a program that contains a process which is shutting down forever. We have to tell the program, we have to tell the process that the shutdown is done, so we need a final return of the shutdown. So that's it, that's cool. That's fine. So we have closed the pipes. As soon as we are shutting down. Okay, that's cool. Fine. Cool. So this is the first task is done. We have 4 things to do: pipe, fork, duplicate, and then execute. So we have created pipes, but now we have to define. That's a good example. For example, the following program creates a pipe and then forks to create a child process. The child inherits a duplicate set of file descriptors that refer to the same pipe. So we have duplicated the pipes after the fork. After the one thread has forked the process, then we have the same file descriptors here. After the fork, after the fork, each process closes the file descriptors that it doesn't need for the pipe, because the pipe creates a pipe, a unidirectional data channel. So this, if I use this function, then I get 2 file descriptors. A write file descriptor and a read file descriptor. So in one process this does not make sense. But after the fork we make a copy of both of them, and each side only needs 1 of the file descriptors. And that's the reason why after the fork each process closes the file descriptors that it doesn't need for the pipe. The parent then writes the string contained in the program. Okay, so this is just example specific, but that's in general. Okay, and you can see if we fork, if we have a failure, then we exit, fine. If we are not allowed to do this in our program, this is very bad. You should be very careful. There is only one special situation we will see today at which we are allowed to use this exit function. At no other place in the system we are allowed to use this function, and this place is in this minimal example. It's okay, but we are not allowed to do this. We are only allowed to do it in this section. Oh, that's interesting. Why is there what? That's an underscore. Terminate the calling process. Terminates the calling process. That's interesting. Cool. We also want we do not want to use this, of course. But in this section, we are allowed to use the exit function. Okay, first things first. We create the pipes. Okay, then we go to the next thing that is forking. We go to the next step, which is forking. Then next page. Fork creates a new process by duplicating the calling process, making a duplication. The new process is referred to as the child process. The calling process is referred to as the parent process. The child process and the parent process run in separate memory spaces. At the time of fork, both memory spaces have the same content. Memory writes, file mappings, and unmappings performed by one of the processes do not affect other. So memory writes, if we write from this thread to this data area, then this data area of the parent process is not affected. The child process is an exact duplicate of the process except for the following points. The child has its own unique process ID, and this PID does not match the ID of any existing process group. So we have a separated process ID, which is different to this ID and this ID. The child does not inherit the parent's memory locks. Okay, I don't know what this is. Process resource utilization and CPU time counters are reset to 0 in the child. Makes sense. The child set of pending signals is initially empty. Okay. The child does not inherit semaphore adjustments from its parent. Okay. The child does not inherit process associated record logs from its parent. Timers, yes, okay. Outstanding asynchronous IO operation from its parent. Yes, okay. The process attributes in the preceding list are all specified in the parent and child also differ with respect to the following Linux specific process attributes. Yes, that's okay. No, the following. Oh, the port access permission bits. Okay. Okay. Note the following further points. The child process is creating with a single thread, the one that called fork. So this one is created. The entire virtual address space of the parent is replicated in the child, including the states of mutexes, condition variables, and other pthread objects. The use of may be helpful for dealing with problems that this can cause. This is essentially what I said, that we have to be careful what we are doing here, because we might see locked mutexes here, locked by other threads. So if we want to use the entire thing, depending on what we are doing, we can make some kind of callback function, I think. In this case, we are only executing another program, so we are not using this at all, because this will become another process, not another process. It's the same process, but another program. Exchanging the content of this thing is done with the exec function. So, After a fork in a multi-threaded program, the child can safely call only async signal safe functions. Until such time as it calls this. A family of exec. The child inherits copies of the parent set of open file descriptors. The child inherits copies of the parent's set of open file descriptors. This means all the file handles. Each file descriptor in the child refers to the same open file description as the corresponding file descriptor in the parent. This means that the two file descriptors share open file status flags, file offset, and signal-driven I/O attributes. The child inherits copies of the parent set of open message queue descriptors. Okay, not interesting for us. The child inherits copies of the parent set of open directory streams. Yes, okay. So that's it. It's just a copy and only one thread. Okay, so and this thing may throw an error. So the return value on success, the PID of the child process is returned in the parent. The PID of the child process again, slowly. On success, this function, on success, the PID of the child process is returned in the parent. So the parent has multiple threads, and one of these threads is at a certain point, at a certain program counter, a certain program position in the code. This PC is the program counter, the position in the code. And one thread is at fork, at the function fork. And if we execute this function in this world, in this process, the return value of fork looks like has the PID of the child process and 0 in the child. That means if this thread is at fork, then the whole process gets copied, and this thread, this means we are at the same location in the code in this process and in this thread. So we are exiting the fork function in this thread and in this thread as well. But the return value here in the parent process of fork is the process ID of the child. This process ID. So the return on this side is the process ID of the child, and on this side, if the thread 1 of the child process is moving on, then we have a return value of 0. On failure, -1 is returned. In the parent, no child process is created, and error is set to indicate the error. So we have a certain thread, we have some function, some system with multiple threads, and one of these threads is coming to this point. And the first thing in the parent is we check if this thing is lower than 0. We check if we have an error. If we have an error, then we say could not fork process, a string of the error. We are moving out of the process, and we shut down the process. We have created 3 pipes, and these pipes get closed. But if we have no error Then we check if the process ID is bigger than 0, then we know that we are the parent at this point. So at this point we can be either in the parent process or in the child process. And if we see a process ID, ID child. Yes, that's better to call this MID proc child. Yes, yes. I want to call this MID proc child. Fine. ID proc child, and here I want to call this say res. If it's more, if it is bigger, then we say the process ID of our child is the result. Otherwise, we are in the child and we do not have a process ID. And that's cool. ID proc child. I think that's it. Yes, that's fine. And the ID proc child is 0 at the beginning. Or -1, let's call it -1. Ah, that's a PID. I don't know if this is an integer or not. Okay. So we have -1. -1, this must be, it can be -1, of course. This means we initialize this thing as -1. Okay. We execute the fork function. We have an integer. I don't know if this is possible. Okay. It seems to be an integer. Okay, whatever. Fine. Good enough. Okay. So this means if we are in the parent, we save the child process ID and we move to the state parent. So this is our world, the world on our side, on the parent side. The child, however, is moving in the child view. We see that the fork returns 0. So there was no error, but we are not in the parent because the fork function returned 0 at this point. So the next thing we have to do is, yes, we have to initialize the parent. Parent start, let's call it parent start. And after parent start, we move to parent. what are we doing in parent start? We close some stuff. We close the sides of the pipes we do not need. That is, we say, at this point we must have three valid pipes created, otherwise we would have an error. So we have three valid pipes. The first one is used as standard in. This means from the parent side we close we want to write from the parent to, we want to use this pipe to write from the parent to the child. This means we do not need the read file descriptor in the parent. The read file descriptor of standard in is not needed in the parent. So we close this thing. Okay. Let's do it. If I think that's okay. Pipe init, pipe init. Pipe initialize. I think that's better. I think that's better. Okay. Dot, and then close. We want to close the pipe, so this means, and we want to initialize the pipes. This means, and we want to close. We want to close the entire pipe in the shutdown function, but we only want to close one file descriptor. File descriptor close of the read side of the standard in the parent. On the other side, for standard out, the child is sending us information, so we don't want to write into this pipe, and the same for the error. Okay, fine. Similar in the child, the first thing we want to do is to close the file descriptors we do not need the same way, but just the opposite version. We in the child we do not want to write to our input, and we do not want to read from our output. So what did we do now? At first we have created 3 pipes, then we have made the fork which duplicated the pipes, and then both processes have deleted the side of the pipe they do not need. So this is cool. Now, next thing. Is the clone? Let's look at this thing. I want to make a doc of notes and note. File exec. So all of these, this whole section should be, yes, moved. That's cool. I think this will be a very big class. Okay. Pipe close, pipe init. We will be able to send a signal to our child. We are able to get the PID of the child. Should we call this? Okay. Let's keep it that way. Fine. Now, what do we do next? We have a new process, the child, with the pipes, and some of the pipes, we have closed the file descriptor of the pipes we do not need in the child. So we have we have left one read file descriptor for the standard in, and we have left 2 write descriptors for standard out and standard error in the child. And now we want to get rid of the standard in, standard out, and standard error file descriptors with the duplicate function. This is if all of these file descriptors are pointing to some file in the system. And we want, if this process is writing something to standard out, then we don't want to use the same standard out of our parent, because the parent does not want that the child is writing into its standard out, but it should use the pipe. So we are taking the file descriptor of the pipes and we are copy the reference to the standard in, to standard out, and to standard error. So that's it. Okay. 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 Let's read the duplicate function. The duplicate system call allocates a new file descriptor that refers to the same open file description as the second descriptor, old file descriptor. Okay, the new file descriptor number is guaranteed to be the lowest number file descriptor that was unused in the calling process. Okay. We will not use the first function. We need the second function. But I want to read the first function as well. After a successful return, the old and new file descriptors may be used interchangeably, since the two file descriptors refer to the same open file description. They share file offset and file status flag. For example, if the file offset is modified by using exec on one of the file descriptors, the offset is also changed for the other file descriptor. The two file descriptors do not share file descriptor flags. See close on flag, the close on exec flag, the close on exec flag, see blah blah blah. Okay, so we do not need this, but the important thing is that with duplicate we can get another file descriptor that is pointing to the same file. This is the property of this function, the use of this function. Now, but we need this function. Why? The duplicate two function system performs the same task as duplicate, but instead of using the lowest numbered unused file descriptor, it uses the file descriptor number specified in new file descriptor. In other words, the file descriptor new fd is adjusted so that it now refers to the same open file description as old file descriptor. So here we get a new file descriptor based on the old file descriptor. And here we have an existing file descriptor, and we want the old file descriptor to be, we want the new file descriptor to point to the same as the old file descriptor. Okay. If the file descriptor new FD was previously open, it is closed before being reused. So the new file descriptor is closed if it was a file descriptor. The close is performed silently. Any errors during this close are not reported by duplicate. That's fine. So we are overwriting this new file descriptor. The steps of closing and reusing the file descriptor in UFD are performed atomically. This is important because trying to implement equivalent functionality using close and dup would be subject to race conditions whereby NewFD might be reused between the two steps. Such reuse could happen because the main program is interrupted by a signal handler that allocates a file descriptor, because a parallel thread allocates a file descriptor. Note the following points. If old file descriptor is not a valid file descriptor, then the call fails. A new file descriptor is not closed. If old file descriptor is a valid file descriptor and new file descriptor has the same value as old FD, then loop does nothing and returns new FD. Okay. So, how do we use this thing? Quite easy. We just say duplicate to. We want the old file descriptor. It's a strange naming. The old file descriptor, in our case, it is the standard in read descriptor should be moved to standard in. So the standard in, I think it's called file number standard in. Let's see if, come on. I don't know. I think it's called file number standard in. Standard in file number. Yes. Yes. So we have in the include stdio we have standard in, standard out, standard error, and these are file stream pointers. And on program startup, the integer value, integer file descriptors associated with the streams standard in, standard out, and standard error are 0, 1, and 2 respectively. The processor symbols are these, so we have to use these. These are the file handles. So our pipe, the read file descriptor, we have closed the write file descriptor for standard in because we do not use it, but the read file descriptor should be moved to this one, and this one should be closed, and we should you should read it like this. This thing is closed and this should be used instead. So for the read we have this, then for the write out we have out, and for the error we have error. So this means we close these things, cutting the possibility to write to the parents standard out from the child. We close this thing, so we are not able to use them anymore, and instead we are using the file descriptors of the pipes. So the child process is using the pipes, and then the parent is able to use the pipes and is able to communicate with the child, giving the child move information into the child and get information out of the child. So this is done. And I do not check for any errors because I think we can't have any errors. Old file descriptor isn't an open file descriptor. This should not be the case. This is a valid. At this point, these three are valid. We have done one error check. I think we do not need a second one. New FD is out of the allowed range of file descriptor. This is not the case either because we are using these macros. Visit Linux only. This may be returned by during a race condition with open. What? With open and dup. Okay. I don't know. Okay. E interrupt. Call was interrupted by call by a signal. Only for dup3. Yes. Okay. The peer process limit on the open file descriptor has been reached. Ooh, what? The pair process. Okay. You know what? Whatever. If, and that's the special thing. We should not use just one. That's bad. If we are not able to duplicate the file descriptor, then we exit. But I want to. The first thing I want to do is to create the error channel. If this is not possible, then I have to leave the application. But from this moment, I can at least cry for help to the parent if I'm not able to create a duplicate standard in and standard out. Then I can cry for help with standard CR because now it's available, and I can say could not duplicate FD std in, and the reason is std error of error number and then I have error number. The same here. Std out. And we are able to tell our parent if we were able to. Could not execute were. File. It's called file executing. Could not execute file. The reason file command could not execute file command because of error. And then we exit. And this we are allowed to use exit here because this is not a usual program in our point of view. We have a special system structure here, and in this, at this point, usually we have the state machine structure, everything is fine and everything is the same all the time. But if we have created a child, then at this point we are kind of like we are in a new process, in the child process, and we are kind of in a new main. And so this is a minimalistic version of a program and has nothing to do with our structure. And this is the reason why we are allowed to use an exit. Was not declared. Why? Because we have IO3. Okay, oh, my ear is itching. Okay, so that's it. So we are duplicating the error file descriptor, and from this on we can send data to the error file, and then we can move out. This is quite cool. This is quite cool. Okay, one moment please. I'm back in a minute. Okay. Yes. I have to improve this application. Ooh. Ooh. Yes. We should not use not use the T-clap stuff. Do we need this? I don't know. We do not need T-clap. Environment. Do we need an environment? I don't know. We don't need the arguments. We do not need an environment. We do not need an environment mutex. Do we need this thing though? Don't think so. This is a very small program. We have an application close request. We have an error line print. We don't have a special argument parser. Oh, be careful. Yes, come on. Okay, that's fine. Yes. No, yes, no. This is 3 and this is false. Okay, that's okay. Standard IO providing. Again, let's try this. So I want to remove this special this high level argument parsing. I want to remove the parser and I want to say that for size ti is equal to 1 and I is smaller than the argument count minus 1. Nah, that's just it's. The first argument is the no. Yes, this is what I want. The first argument is always the program name, so we have to. Yes, we have. Yeah, that's okay. Plus I, and then I want to make the out of argument value I and an end line. Hopefully this is working. Different signedness. Yes, okay, whatever. Arg exception. Yeah. Oh, yes, of course. try. This is so strange that this is working. That's a cool tip from Gyroskaya. Okay, so it's working, and if we execute Ninja and standard IO, yes, so that's fine. If as you can see, it's giving us one line of the line of the first argument, which is the program name, and then we can say argument 1, and then we see argument 1. If we have argument 2, then we have argument 2, and this program is also able to test. We can, and that's the cool thing, we can move into the standard input. This is the pipe symbol, moving this elements into the program, and we can argument 1 and argument 2. If we are executing this test, then we see it's printing the arguments immediately, and then every 5 seconds it's printing the lines of the standard input. So we have the arguments immediately, then we have the first standard input line, and then we have the second one, and then it has finished. So we are able to, with this special program, we are able to test standard input, standard output, standard error, the signals, and the arguments. Fancy. Fancy, fancy, fancy. 2 hours. 2 hours, and we didn't do anything at this point. So, file executing. Okay. File execution testing. At the moment, we are creating the file execution process, and then we are starting the file execution process, but this is not doing anything. Okay. So we want to execute a program. How can we do this? By setting its command. Now let's set the command to, we are in the file executing directory, we go back 1, we go back 2, 1, 2, and then we go to standard IO providing, and then we say build native, then we say standard IO, okay, that's the program we want to execute. And we want to execute, yes, what should we see? Let's make a call to a program that does not exist. We say the success is equal to the execution success. If success is equal to pending, then we break. If the success is not equal positive, then we say error executing external process. Error executing file. Test one, yeah. So we check if we have this. Okay. So the expectation is that is that nothing is happening. The program should just run, I think, because we are forking, and after forking the child is doing almost anything, so it's fine. But during execution, the child sees that there is an error. It executes with exit failure. It tells us it was not able to execute the file, but the parent is not consuming anything. It's just closing the file handles and then it's doing nothing. So this means we should be stuck in this state, and that's it. It was forking, fine. So I try to split the terminal to something useful. At first, on the bottom side, I want to go to standard IO build native, yes. This is the test program, and I want to see that localhost 50/50. No, it's not 50/50. Yes. We see something. Fine. Yes, that's it. Okay. We start the test. We see the state of the IO providing process. It shows the line. It has a line delay. Then it shows the line, and then it stops. That's fine. Okay. Meanwhile, in the file execution test, we can check localhost 5000, I think. Yes. We are waiting for the test to be finished. Okay. So the next thing we have to do is parent start, and then we have parent start, yes, and then the next state of the parent is to state child supervise. No, come on. State child supervise. Supervise. Überwachen, betreuen, kontrollieren, leiten. Yes, yeah, supervise. That's cool. So we have to supervise our child. What should we do? We should check if there is. What can we check? Yes. This is a cool explanation, I think. Somewhere there is a cool explanation. Ooh. It's not this post. That's not what I want to see. File execution. Pooh. Different version of execution C and C. Yes, that's it, I think. That's it. Yeah, for questions like this, always read the source code from glibcs. That's so cool. That's very cool. That's a very cool. A link. So we should be able to see in the glibc, hopefully there is a directory called nptl. Then we should have systems. Oh no. Oh, okay, maybe. Oh, maybe we have to. Oh, yeah. Maybe we have to configure. Configure this. I'm missing a 2 old GOG. Checked into the bar. Yes, that's important, of course. No, I will do this someday else. But nptl. Oh, GitHub. Oh, that's cool. Oh, that's cool. Look fork. Okay, this is. I have to check what this thing is. Okay. Okay, that's a different story. We supervise the child. We supervise the child, so we need the wait function, I think. So we have executed the program. More details on that later. We have 2 hours and a half already. Okay, this is what we can do. What is the wait function? All of these system calls are used to wait for state changes in a child of the calling process. And obtain information about the child whose state has changed. A state change is considered to be the child terminated, the child was stopped by a signal, or the child was resumed by a signal. In the case of a terminated child, performing a wait allows the system to release Yeah, that's very important. In the case of a terminated child performing a wait allows the Linux system to release the resources associated with the child. If a wait is not performed, then the terminated child remains in a zombie state. See notes below. A child that terminates but has not been waited for becomes a zombie. The kernel maintains a minimal set of information about the zombie process, PID, termination status, resource usage information, in order to allow the parent to later perform a wait to obtain information about the child. As long as a zombie is not removed from the system via a wait, it will consume a slot in the kernel process table. And if this table fills, it will not be possible to create further processes. That's very important. If a parent process terminates, then its zombie children, if any, are adopted by the init process. So if I die and I did not wait for the child's, then the children get assigned to the init process, or by the nearest sub-reaper process, as defined through the use of cool. And I did not. This is the first time I see the word sub-reaper. That's cool. Automatically performs a init automatically performs a wait to remove the zombies, because the wait, what is wait doing? If it gives me the return code of the child, but if a child executed and terminated, then the return code is stored in Linux, in the kernel. And the parents have to collect this information, this return information. But if they do not with the wait call, then the Linux is not able to delete the children, because maybe the parent is collecting this information later on. It's very important. But if I'm not collecting the information of the children, from the children, then, and I as a parent process, I die, then the children get assigned to the init process or the sub-reaper. And this thing does not use the return code at all, so it's automatically removing the zombies. It's waiting for everything, because I don't care about, as a sub-reaper process, I don't care about the children and the return value of the children. That is a very, very cool thing. That there was a very, very interesting story about this thing for me personally. That's so cool. Okay, this can be a trap. This can be very dangerous. Okay, so we have different wait functions. The wait functions do something. Okay, we have function wait with a status. We have the wait PID function with PID, status, and options, and we have the wait ID. ID type, ID. This is the C-limit interface. C nodes for info. Okay, let's see. Conforming to POSIX every function. Interesting. wait ID. This is wait process ID. So we have a process ID, and here we have ID type, ID, and info operation. Okay, what's that? This is the glibc and POSIX interface on the raw system call. Wait ID, the wait and system call available system provides more precise control over which child state changes to wait for. Selects the children to wait for as follows. Wait for the child whose process ID matches ID. Wait for the child referred to by PID file descriptor specified in ID. Group ID, I don't think we need that. Okay. Okay. What's the difference between wait and wait PID? All of these are used to wait for state changes in a If a child has already changed state, then these calls return immediately. Otherwise, they block until either a child changes state or a signal handler interrupts the call. So otherwise they block. We do not want them to block. So blocking is very bad for us. Assuming that system calls are not automatically restarted using flag conjugation. Okay. In the reminder of this page, a child whose state has changed and which has not yet been waited upon by one of these is termed waitable. So if a child whose state has changed and which has not yet been waited for, we are waiting for state changes of the child, is waitable. This means a zombie process is waitable. So wait and wait PID. The wait system call suspends execution of the calling thread until one of its children terminates. The call wait is equivalent to wait PID. Okay. -1. The wait PID system call suspends execution of the calling thread until a child specified by PID argument has changed state. By default, wait PID waits only for terminated children, but this behavior is modifiable via the options argument as described below. The value of PID can be, so the first, this call is the same as this call. What does this thing mean? Can we use this function? -1, meaning wait for any child process. That's not what we want. So the conclusion is that we cannot use this function. We don't want to use this function, so we have to use this function. 0, meaning wait for any child process whose process group ID is equal to that of the calling process at the time of the call. No, we do not want this. Bigger than 0, meaning wait for the child whose process ID is equal to the value of PID. Yes, that's what we want. So this thing has a PID as result. Yeah, okay, not result. Pipe, fork. let's make another variable PID type ID proc, and pipe has a result, and fork is the ID of a process. Yes. ID of the process is MID process of child. So we should be able, file executing, we should be able to execute. No work to do. Yes, that's possible. Okay, this was working. Okay, fine. And now we can reuse this thing in the parent. Child supervisor. ID of the process is wait process ID. Which one? The process ID of our child. So we only want to wait for one child in our process. So the next thing is what kind. So we have the next thing is status. How the status we get. That's the result. And then we have options. Value of options is an or of 0 or more of the following constant. Return immediately if no child has exited. That sounds good. Untraced. Also return if a child has stopped, but not traced via ptrace. Can also return if a stop has been resumed by delivery of the continue. We always want to return. The following constant. Return immediately. Also return if a stop child has resumed delivery of the count. For Linux only options, see below. If this is not null. Oh. Yes, because that's a pointer. Yes. Okay. If this, that's a pointer to a status. Yes, that's a pointer to the status, yeah. If this status is not null, wait and it will store status information in the int to which it points. This integer can be inspected with the following macros, which take the integer itself as an argument, not a pointer to it, as it is done in wait and with PID. Okay. Okay, returns true if the child terminated normally. That is by calling exit or this exit, or by returning from main. Returns true if the child process was terminated by a signal. Returns the number of signals that caused the child process to terminate. Returns true if the child produced a code dump. Returns true if the child process was stopped by delivery of a signal. This is possible only if the call was done using untraced or when the child is being traced. Returns true if the child process was resumed by delivery of sig continue. That's confusing. This sentence is confusing. This integer can be inspected with the following macros, which take the integer itself as an argument, not a pointer to it. So if no, I don't want to check. I don't want to check. No, I want to check. Returns true if the child process was resumed by delivery of seek cont. Stopped. Let's try something. Let's try something. We have the file. What? Why? Okay. I want to see. Oh, come on. File executing. File executing. I want to see. Config proc disable tree default. No. I want to see everything. Disable. I want to see everything in the unit tests. Everything but the debugger. Yeah, that's fine. So that's cool. Oh, almost. So wait, PID was not declared. That's fine. Signal. Oh, come on. That's cool. And now I should be able to see. Yes. File execution testing. And as you can see, because this is the parent, we are in the state child supervised. And now I want to do something else. I want to supervise the child. I do not want to hang in any way. So this means the options is an or 0 or more of the following constants. We have used all of them. And now, for example, I want to see if I want to check if stopped res. Oh yes, no, yes, that's fine. I think res, yes, okay. Then I want to have a string that is called state child. String state child. Let's try something. The child state of the child is running after running if we have started the child. And then we have the dinfo state child C string. Okay, let's see. Let's see if this is working. Fine. Oh, the. Okay, the state of the child is running. Cool. If. Oh, that's this compiled. Oh, that's strange. Oh, this can't be true. Okay. Maybe it's using this one and we don't have a fall through error. Oh, come on, that's strange. That this is compiling. That's strange. Okay. Let's check what happens if returns true if the child has terminated normally. Okay. Let's do this. Terminated st child supervise st child done. Yes, I produced the fault through, yes, and I have deactivated the warning for the fault throughs. You're right. So if the child has exited, then I want to indicate this by child done by terminated. Let's see if this is working. And then we say break, and then we say mState is equal to done. Let's see if this. I think we should be able. We should be in the state done. Oh no. Okay. This is strange because we are in the state child supervise. We are in the state child supervise in the parent. As you can see, we are supervising the child. We have, we do something else as well. I want to see the process ID of the child. Yes, here, state child, ID child, and then we say yes, of course. So we have a certain process ID. Oh, come on, what? Okay, kill. No such process. So it's kind of behaving how I expected, but not entirely, because we have this process ID. That's fine. We have used fork, and we in the parent process we got an ID, a child ID. So we are in the parent process. In the parent process, we moved after the fork. We got a child process ID. We moved to the state parent start. We closed the pipes, and then we said our state should be running. At least it was forked and it should be running. And then we are waiting for a change in the child state. So this should be executed every time we have a certain ID for a child. That's cool. And then we should be able to see if it has terminated. And it should have terminated. Let's see. Using command what? Yes. A file which is not existing. So if this file is not existing, then we should be able to fork. In the child, we should be able to change all that stuff. But, and this is the thing, we should not be able to execute this thing. And this function return value, the exec function returns only if an error has occurred. The return value is -1 and error is set to indicate the error. So this should be the fate of the child, but then the child and this is kind of true because I didn't see the PID, so that the child terminated. In fact, the child terminated, so that's fine. But somehow the parent was not able to see this thing. Okay, let's see what wait is doing. The return value. Wait on success. Returns the process ID of the terminated child. On failure, -1 is returned. On success, no, we are not using this, we are using this. On success returns the process ID of the child whose state has changed. If no hang was specified and one or more children specified by PID exist, but have not yet changed state, then 0 is returned. On failure, -1 is returned. So I try to do the following. If not, this, then break. But if this has to be done before, if ID process is smaller than 0, then we have an error. Proc error log could not wait for a child. And now we can do something that is cool, because we can say, we can make a log state state of child changed. Okay, that's it. So the thing what I expect is that we should see at least this log message. Then we are one step further. Then the next thing is we may have checked the wrong state yet. Oh, okay, it's executed all the time. Could not wait for a child. What? Could not wait for child. Yes, because Yes, because this was an and error now is not equal to okay, now that's could not wait for child. Why? No child process. What? Let's make head. What? Forking using command state of child changed. Okay, the first thing we have is not an error. The first thing is not an error. We have a changed state, of course, because it terminated, I think. And then cool, yes, but then that is the yes, that's the reason why it's always a return, or it's not exit. Yes, that's it. That's that's the behavior I want. This means we have a file executing process. The change at the state of the child has changed, but now we are not consuming. We are not checking every possible state, so the code is not finished yet, and that's the reason why we have. Checked the wrong state and then we try to check again, but at this stage the client is not living anymore, of course, and then we get the failure, could not wait for child. That makes sense completely, so everything is fine. We should do something like this. I want to be super careful. I want to check for an error. I want to check for an error. An error that is not pending error. And then I want to check if I do not have an ID, or the ID is smaller than 0 and it's a pending error, then break, and otherwise, okay. Okay. We have what's that? Linux nodes, yeah, nice, cool. Okay. So we have a yes. Returns true if the child terminated normally. Normally, that is by calling exit. And we did this. I think we did this. Let's do something else. Let's use at one moment. Let's use the standard in, out, and error of the parent. So we should be able to see what is going on. No. No. Let's test again. Test. Yes, we see. So this is a message from the child. This is a message from the child. So this is cool. And we should be able to see this as well. No. What the hell? Let's make something else. Child A. Child B. Okay, this is fine. Read. This is working as well. And now duplicate. Okay. I'm so stupid. I'm so stupid. This is not what I have to. This is the redirection. So here we have to see out child A. Let's see if we can. We should be able to see this. Oh yes. Oh, that's cool. Ha. Could not execute file as expected. No such file or directory. And then we have an invalid pointer. What? What? This is strange. Invalid pointer. That's at some point I'm using free, I think. At some point. Egg free. Oh, the session is almost over for today. What? This takes multiple streaming sessions. This is okay, but this is not. And I know that I'm using free somewhere, but it's in this process, I think. Free. Yes, I'm using. Yes, but that's fine. That is fine. That is fine. No such file or directory. Okay, no such file or the. Ah, yes. Okay, fine. Exec could not execute file. Yes. Ah, oh yes. What? No. What? Okay, I do not understand this. This line is strange. This is the child and I'm exiting the child. Who is telling me if I am redirecting the output to the parent, then I don't see the free line, but so this must be a message from the child. Invalid pointer. This must be a message from the child, but I don't understand why the child should give me this, because I get this message, which is fine. Error number. This gave me an error, and then I'm exiting immediately. Maybe it's because I have file executing. Maybe it's because of the signal. I have a signal handler. Yes, maybe this is the. Let's see if. Maybe this is the reason. Can I get a fork? Forking. I want to see the child ID. ID child. Is equal to I want to see the child ID in the log, because then I want to, in the application close request handler, I want to see get PID. Man, get PID. Yes, Ionic standard. Oh, that's cool. Oh. PID, come on, handle. My ID and parent ID. Oh, come on. Parent ID, get PP per ID. Yes, okay. ID check. No, damn it. This is the parent telling us using command stdio2. Then the child tells us could not execute file. Fine. That's I don't understand this. I don't understand this line. Oh, boo, boo, boo. That free makes me sad. I don't know why this. I don't have any free. Maybe I don't know. I don't know. Exit. Okay, whatever. So, at least the child is terminating as expected. It's terminating as expected, but has changed. Okay. Okay. One moment. File executing. So I want to stay in this state even though we have an error. So this should stay, and then we have because I want to check the terminated state. That's temporary. The cool thing is we have a child ID in the log. Ah, yes, yes, that's cool. My ID, yes. This, why didn't I see this? Ah, okay. But this is very important because oh yes, yes, this is not good. This is not good. Yeah. Oh. Uh. Ooh. We have to. That's an important thing. That's an important thing. What about the signal handlers? Signal. Fork. Handlers. Clone. Signal. Okay. These system calls create a new child process in a manner of similar to fork. By contrast with fork, these system calls provide more precise control over what pieces of execution context are shared between the calling process and the child process. For example, using these system calls, the caller can control whether or not the two processes share the virtual address space, the table of file descriptors, and the table of signal handlers. These system calls also allow the new child process to be placed in separate namespaces. I want to unregister this signal handler in the child. We need it in the parent process, but I want this thing. And who, at which point do we have to do this? That's that has to be done in the child because we are using fork. It has to be done in the child. Later on, we would be able to specify in the clone command that we don't want to share the table of signal handlers. So we need the signal, the man page of the signal. Signal, no, this one. Okay. Warning, the behavior of the varies across. Avoid this instead. What? What? The behavior of signal varies across Unix version and also varies. Avoid this, its use. Okay, interesting. Okay, that's something for later. Boah. Okay. So that's for later. I want to unregister this thing. Handler. Warning. Yes, fine. If this is delivered to the modem, I think I have just to send null. Handler. returns the previous value of the signal handler on failure iteration. I think we should be able to make something like this. I don't know. Hopefully this is removing the free error. The child is unregistering the signal handler of the parent, because the parent let's see. Okay, we managed to unregister the handlers, what was very important, because the child is not allowed to execute this signal handler function from the parent. No. Ho. Still it's fine. Okay. So if yes, the child has terminated already, but we don't have an output of the signal handler function, and if I press Control and C in the parent, then we have the parent ID, and as you can see, this was the ID of the child, and we don't see the ID of the child, so this is fine. Okay. So this function is not executed anymore in the child, but still we have a free pointer, and I don't know why, because could not execute file. Yes, because if I think I'm not able to shut down properly in this situation, because we have, I think if we make an exit here, let's try something. We should see, let's make a message IO stream. What if I see out destructor? If we see this, and we should, yes, we should be able, yes, std, of course. What? Why? In the child, is this thing executed? It should be executed, I think. I think this must be executed. If we make an exit, then the whole application is... Let's see what's happening if... Let's see what's happening if we... Oh. Oh. Oh, this is not what I wanted. Okay. I think I produced a fork pump unintentionally. Okay. Let's do something else. We are in the fork state because we are in the fork state. We should at least move out of the fork state by... So the child was... All the children were telling us that... Yes, as you can see. That's cool. Yes. Mm-hmm. I don't see any chance to fix this situation. If we create a child and this child is the result of a fork, then we have in any system, in a system of any size, we have this thing without all the other threads, some special combination, and if this thing wants to make an exit, then all the destructors are executed, I think. But why I should see this line. I should see this line. File executing. Yes, not in this case, of course. Not in this case because I'm not... Maybe this maybe it's... let's see. No invalid pointer. So I have to check. I cannot guarantee that I'm not able to shut down the application properly with only one thread. It's not possible. I can do an exit. But that's a very interesting thing. Okay. I don't know how to fix this. Okay, at the moment. So, our child has changed the state forking. This is the parent telling us it was forking and then using the command. The child told us could not execute file. And then it was crashing because of the exit. And then, it was crashing, invalid pointer. Maybe this is the reason. Maybe that's the reason. Okay, because we did not shut down properly. Maybe. If the child was terminated by a signal. Yeah, let's. Okay. Maybe this. Parent start, child supervise. Yes. If result. If it was signaled, then terminated by signal, terminated by exit. Okay. Terminated by signal. Okay, this was the reason, because it crashed. The child was crashing during the exit, so this is okay. And then now we are in the state child done. Okay. And as you can see, shutting down. No, that's fine. Okay. Child done. Who? Terminated by signal. If it was terminated by signal, yes. Let's make an integer called m. Okay, signaled. State child. ID state whatever. Okay, yes, terminated, of course. And we want this thing to be signaled terms and returns the number of signal that caused termination signal. Okay, the termination signal was 6, and then Linux signal number sig abort. That's expected. Okay. Because there is a 43. Okay. So whatever. Okay, we check if exit state, signaled, core dump. We do not care if this thing has dumped. Core dump. This one should be signal true. Is not specified in and is not available on some Unix implementations. It's used under if def v core dump. Because at least we should, yes, we should check this thing. Core dump if it's not harmful if we say dump core, and at least we say that the child is finished. Because I don't know if we get this thing, then the child has terminated, but I don't know if this is executed as well and this. So I'm just doing the same thing. Okay. So stopped. Returns true if the child process has stopped by delivery of a signal. Okay, that's cool. Okay. If it has stopped, I don't care. The child is not for me it's not done, but at least it stopped. That's fine. And stops it, returns the number of signal which caused the okay, then fine. Let's save this thing. this information. And continued. So, okay. How can I stop? I want to stop this thing. Signal. Stop. Stop. Makes sense. Okay. That's cool. And then stop and then continue. Sig stop. Sig continue. Okay. So now I want. I think that's the last thing I will do. That is the testing should try to execute something that is yes, as you can see, we have executed the function standard IO and it is waiting, I guess. It's running. Supervise. We did not get any state change, and now we should be able to make a sig stop. Stopped. Child state of child has changed. Yes, and then we say sig continue. And then it is running again. So we have, at least we have the ability to supervise the child process. We can see if the child has been stopped, terminated, continued. That's quite cool already. So our parent process is, and then we say sig stop I don't know what kill man kill kill. I have, there is, I don't know why I'm doing it, but sometimes is this the application? Terminate the process. Yes, signal. And there is the possibility to make okay. Linux signal number. Sig kill. Okay. Terminate. Terminate is terminate. And sig kill should be kill maybe. Okay, let's see. Stopped, and if I say sig kill, terminated by signal 9. That's the reason why I'm we can make kill -9. Oh, that's the reason why I'm doing this. Okay, let's do it this again. It's running. I can say sig terminate. What? It's not terminate. Software termination sent by kill by default. A software termination. Maybe because our if a process sets this in, it must be quit immediately and will not perform any cleanup operations. Software terminations. Okay. We do not have any handler. Okay. Maybe this is the reason. Okay. Sig stop. Stopped and sig continue. We are still supervising the child because we see that the child must be running still. How can I to send an interrupt signal? Interrupt. Let's try to make an interrupt. It's not doing anything. Yes, kill and interrupt. What if we make a user? Sig send is user. Yes, let's call this sig user 1. Sig user 1. Okay, this is a message of the child that's implemented. We have registered a handler for this user interrupt. So the child is still running. Oh, let's try something. Let's try this. We stop the thing. And then I want to see what is happening if I make the user. Oh, it's not doing anything because it stopped in the kernel. Stopped. What if I continue now? I think the signal should be in some kind of queue. So if I continue the process, I expect to see this line. Oh yes. Okay. Ooh, it was terminated by exit. Why? Interesting. I say sig stop. I say sig user. I say sig continue. Yes, no, that's fine, because no, I don't understand why it was terminated. Stop. User. maybe the interrupt. Stop. Okay, I don't know. Yeah, cool. So these are kill. Wait. These are the no hang, wait. Okay, oh, that's interesting. Wait ID. Okay, now so we have, I think we have you checked all the flags. Okay, let's see. Exited, normal exit. If normal exit, then save the status. Signal, if it got the signal, terminated by signal, then save the signal. Core dumped, if core dumped, then ooh, that's, okay, that's bad. So okay, core dump returns true if the child produced a core dump C, and this macro should be employed only if returned true. Okay. Oh, this means returns true if okay, bool m core child core dumped. Oh, come on. If signaled, then okay. Terminated by signal. State is equal to this, and then we have child core dumped, question mark, if yes, core dumped, otherwise nothing. Okay. Okay, core dumped. Should only employed if this mark is not specified, blah blah. Okay, so then we have stopped. Child is stopped. Stop signal is saved, and stopped is not important for us. Okay. Continued, yes. And that's it. So the supervising process. The supervising stage should be complete, hopefully. We check at first if there is some error and could not wait for child. This is a real error. And then we have the pending state. Okay, this is still running. Okay, that's cool. Stop. Continue. User. Stop. User. Continue. Okay. I think we are done for today because this was a long session and we have done a lot. But as you can see, it's still some work to do. And we have 320 lines already. Oh, that's bad. That's so bad. This will be a big process, yes. Okay, whatever. I think that's important. Okay. I think in the future we may need to use clone instead of fork. Maybe. If we want to have more control about what is cloned. Do we want to have? What do we want to have cloned? Okay. So we have cloned the stuff, we have created the pipes, we can shut down and we can clean up the pipes, we can redirect the pipes, the output to the pipes. So you see that we saw, yes, file executing destructor. We saw the user message, but now we don't see the user message because now I have redirected the output to the pipes already. So theoretically we are able to read stuff from the child. Okay, this will be the next session. Harder than I thought. And we have to consider a lot. Okay. System. Build fork. Oh, I think some frames were dropped. So this is our documentation. We have a parent process. We are doing a fork. We are copying a lot of stuff. The strange thing is we only have one thread, the calling thread, left in the new process. If we want to Ah, come on. I think I may... have a solution. I think I may have a solution. I will try to create another thread that has a clean state. And from this, what do I mean with clean state? This task is running in a very big environment already. A lot of stuff has been created. I don't know. A lot of stuff has been created at this point. If I don't think this is a solution, because if I create another thread, the thread itself is clean, but maybe I can. Yes, we will need to. I think. Oh. Okay. Whew. Let's do something. I want to reproduce this state. Okay, we have this state terminated by signal. Fine, and child done. If the child is finished, then we should... Okay, that's something else. But I want to see if we are able to get rid of this error. This is a fatal error. That's a bad error. I don't want to have such an error. And maybe we can get rid of this error by using clone. I don't think we are able to get rid of this error if we are using another thread, because we may execute and create another thread which itself is clean. It's a clean function, but if we have this thread in here and the thread is exiting, then we still have all the C++ objects in here, the complete process structure from this, from the parent process. And as soon as we execute the exit, then all the destructors get executed, and this is bad. So we have to get rid of the data, of this data stuff itself, because it's not useful to us in any way. No, it is useful. We have to use some stuff. Okay, now whatever. Maybe I have an idea for later. Let's raid someone. So let's raid someone. Thanks for watching, everyone. Let's raid Boomben. Let's raid Boomben. What is he doing? Oh, he's coding. That's cool. Let's raid Boomben. Cool guy. He's making simulations market simulations and stuff sometimes. So let's see what he's doing. See you next time in on Tuesday. Bye everyone. Thanks for watching.